Hello and welcome to our first lesson in actual machine learning. So the first algorithm that's generally taught when it comes to machine learning is linear regression. And linear regression serves as a very good introduction into machine learning and into how machine learning works. If you're able to understand linear regression and what it means to create a model and what regression means and what it means to fit the data set and all of these terms that we're going to become familiar with through linear regression, all the other algorithms are essentially fall into the same paradigm. So they're different in the sense that they're different algorithms, and you're going to have to look out for different stuff, and the way the algorithms work are different, and the mathematical equations behind them are different. But you'll go through the same steps that you would go through, generally speaking, that you would go through with a linear regression problem. So it's very important for you to understand linear regression, not in this mathematical sense, but in the more general, more abstract sense. Like, what are we doing? We are taking a set of data and we're fitting it to a mathematical model, whatever that model may be. In this case, it's linear regression. And then we're using that to predict on new data. So just try and pay attention to this more abstract understanding of what machine learning is. And just think of linear regression as the simple, practical example that we're trying to use to learn this concept, which is machine learning. So having said that, let's go ahead and start. Since linear regression is so important in this regard, I've actually created 3 separate sections for linear regression. So this one is just for us to get a very simple understanding of linear regression. We're not going to be using any frameworks or any advanced libraries and that kind of stuff. We're going to be building this model from scratch using base R, just so we get a sense of how everything works in machine learning. And once you understand that and you get that sense, the following sections are going to rely more on frameworks and libraries to help us with more advanced machine learning concepts and algorithms. So let's first start by defining what a model is. Okay, probably heard me say this word many times, and you're going to hear me say it many times in this part of the course as well, especially in this part of the course, because a model is basically will describe the data set that we want to predict on. So the goal of a model is to provide a simple, low dimensional summary of a data set. So it's essentially a mathematical summary, or it's a summary that can be, it doesn't have to be mathematical, right? Not all machine learning algorithms are mathematical or parametric, right? But it's a summary that you can replicate easily without having to recreate the exact data set. So there are 2 parts to a model. First, you define a family of models that express a precise but general pattern that you want to capture. So here, you don't have to be accurate. You just create a family of models. The models have to be in a way that you know that it's possible to somehow describe the data set if you are more accurate, but you're not trying yet. You're just creating a family of models. And so an example for this family of models might be, a straight line or a quadratic curve, right? If you take a set of data points and you plot it on a graph and you run a bunch of straight lines through it, some of these straight lines will be more close, right? Resemble the data set more closely than the other lines, right? Some lines might be just way, out of the range of the data points. And so that's not a very good model for summarizing this data set. Another line might run right through the data set, right? And that might be a more accurate summary of the model, okay? Or if the data is more complex, maybe it would the family of models would be a family of quadratic curves or any other sort of curve. So, these are just examples. So an equation like y equals, a1 times x plus a2. So that would be a linear line, a straight line. Or y equals a1 times x to the power of a2, for example. This would be a quadratic curve. These are just mathematical equations that describe lines, right? And that's essentially what we mean by a model. So those lines could essentially, if you're able to get it accurate enough, could somehow summarize or closely resemble the data points in that particular data set that you're dealing with. So here X and Y are known variables from the data. So those are the data points that we have plotted on the graph. A1 and A2 are parameters that can vary to capture different patterns. So those of you who have some mathematical background would know that this represents the slope of y of the line, and this would represent the y-intercept. So by changing these two parameters, you're essentially creating different lines that have different slopes and different y-intercepts. And if you generate a bunch of these, right, using a bunch of A1 and A2 possibilities, you'll have a family of models. And some of these models, again, will more closely resemble the data set than others. So this is the first part of finding a model for your data set. And don't worry if these equations shouldn't scare you. I've stated this previously, you do not need to have a mathematical background for this course, right? But, these are not too complicated. So, they should serve the purpose of helping you better understand the somewhat conceptual or abstract definition. So part 2 of building a model is to generate a fitted model. So remember, we created a family of models, right? Plural, many models. And now we want to generate a fitted model by finding the model from the family that is closest to your data. So take the generic model family and make it specific, right? Remember, this was A1 and this is A2 and this is A1, A2. This is the quadratic formula and this is the linear formula. So what we did was we generated a bunch of models using different random numbers, so like 3 and 7 and 1 and 5 and 9 and 6 or whatever, right? And so we're left with, let's say 100 different lines, 100 different models, and we pick the one that is closest to your data. And I'm going to explain in the following slides how you would measure closeness. So what does it mean for a model to be close to your data set? So there are ways to measure that, and that's crucial for us to be able to measure the closeness, or at least the error of the model to the data set. So we would be able to decide on which model to pick as the fitted model. Okay. Now, don't worry if this is still a little bit too abstract for you. I'm going to be, in the next video, I'm going to be going into this practically in RStudio using base R. And we're going to actually be generating these family of models together and picking the fitted model, right? So don't worry. Try your best to understand all of this. So that would be the fitted model, right? The one that most closely resembles our data set. Now, very important caveat is that a fitted model is just the closest model from a family of models. Do not forget that. Okay, a fitted model is just the closest model from a family of models. That's all it means. The best model is the best only according to some criteria, right? You define that criteria. So I mentioned that, there are ways to calculate the closeness of a model to the data set or the error of it. So you want to minimize the error, for example. So that's a criteria that you define yourself. Based on another criteria, you might find that another model is considered the, quote unquote, best model. So, a fitted model does not imply that you have a good model. It doesn't have to be good. It's just the closest from the family of models you generated. Maybe you didn't generate a sufficient amount of models. Maybe you generated, just 2 models and they're both very bad, and the closest one happens to be, termed the best, but it doesn't at all accurately describe the data. But it does have the lowest error out of the 2 models, right? So that's something very important to keep in mind. Just because, you come across a fitted model doesn't mean that, you have now the perfect model, right? It does not mean the perfect model. It does not imply that the model is true. Okay, I'm re-emphasizing this. A fitted model is best only according to some criteria. It does not imply that you have a good model or a perfect model or even a close model to your data set. It does not imply that the model is true. It's just the best among the family of models that you created. So if you do come, in your work, right, when you're working with data and you're trying to, do predictive analytics and machine learning, and you find a fitted model, and you run your data, and you predict your prediction, and you validate your data, and you find that your accuracy is terrible. One of the reasons might be that your fitted model is not actually a good model. So you might want to generate a larger set of models for your family of models, or you might want to change the criteria, or you might want to change the family of models, right? You might want to change, maybe a linear line just don't work with your data set. Maybe your data set is naturally quadratic, and so you're using the wrong family, right? So there might be a lot of criteria like this that you need to think about and consider. So don't rest assured that just because you have a fitted model, you're good to go. The goal of a model is not to uncover truth, but to discover a simple approximation that is still useful. Okay? Don't forget that real data is real data, right? It's not, it wasn't created because somebody, plotted some mathematical linear line and decided to create the data based on that line. It's real data. So it's very unlikely that it's actually represented, or it was actually created using a model, right? So your model is just an approximation, a simple approximation for that particular set. This is something that's very important to drill into your mind, because a lot of people, sort of lose touch with what they're really doing, right? We're not able to know how a data set was actually created, right? Most of the time it's probably random, but it has patterns within it. And we hope to find the best way to represent that pattern from our point of view, but that might not be the source of the pattern itself. So this is a good quote to keep in mind from George Box. All models are wrong, but some are useful. So if it serves the purpose, if we do find that because of the fitted model that we found, we're able to accurately predict, right, to a degree, like let's say 80% accuracy, most of, the new data, it's useful, it's working, right? Instead of a 50% chance of us making a decision, now we have a 80-20% chance of us making the right decision, right? It proved useful. We validated it and we've used it over and over again, and it's useful, but it might be wrong. It might not be the actual representation of that data, but it's useful, right? So that's something important to keep in mind. I would advise you to return to this slide quite often when you're doing actual work out in the field, just as a wake up, as a reminder to what we're actually doing.